Now that we've imported our data set, the next step will be to build our network. And for that, we are going to be using a library called NetworkX right here, which is literally, as it said, it's a package for network creation, structure, dynamics, and all that. Y'all can go ahead and read the different notes they have right here. They have pretty good documentation, to be honest. So I'm gonna leave a link to NetworkX in the description down below, on the text-based version of this tutorial as well. So yeah, so I'm going to be showcasing you in next step just the different steps to create a basic graph. Remember, it's a basic graph, nothing too complicated. I'm going to show you the main functions, and then we'll see where we can take it from there. So first, what you'll need to do, right, once you imported everything, is to import NetworkX and create a graph. So for that, let's go. If you don't have it, I'm not sure if it is already installed, but if it's not, just go to the documentation and see how you can install it onto your Python's into your Python whatever installation. I think if you're using Anaconda, you can conda it. If you're using anything else, you can simply pip it using the command prompt. So we import NetworkX as an X, and then we go call our network. Let's see, network is equal to nx.graph graph. Let's run this. Taking a while. NetworkX as an X. Yeah, perfect. Okay. I thought there was a error. It took quite a while to create. So, right, we have a network right now. It's an empty graph. It doesn't contain anything. So, the first thing you need to do is to insert the different airports as nodes. So, networks have nodes and edges, and the nodes basically are going to be our airports, and the edges are going to be the different routes that the planes take. So let's go ahead and insert the nodes. In order to do that, we're going to use a for loop. So for every airport in our array of airports, which is airports db, I think, airport dash db, we can use network dot add a node. And what do we want a node? A node is basically just how will I, a node basically contains, it's just a container. It contains a bunch of information. In our case, this node is going to contain the airport, the different airport information. And in here, we can add a more descriptive, because in the array, I use just 0, 1, 2, 3, 4, but I needed to comment out next to it what it is actually for somebody else to know. But in our case, we can simply add the different information on it. And as an ID, we can simply use the airport's ID as a node main identifier, and the rest basically we can use a more descriptive name. So let's go ahead. We go row number 0, not row, which is, so we use airport and whatever is contained in the first 0, then we have the ID, which is equal to airport. It is stored in the second slot, airport 1. Make sure I got this right. Then we have what, the name. All right, this is going to take quite a while to write everything. So I guess I'm going to speed this up, and then once I write everything down, I'm going to go on do the same for the edges. All right. Alrighty, here we go. We are done transcribing everything. So you have as a node, and I think I made a mistake here as well. It's not add node, but it's add node. And then we basically added whatever was in the arrays, the different arrays information for every single row within the array of array. We grabbed the information, and it's this exact same information you'll find on here. So we just created a node, and each node will contain as node identifier this number. Then you have ID equals to this. Then you have airport name that's equals to that, country is equal to that, so on and so forth. So basically what we created as a node is going to function kind of the same way as a dictionary, in which you can just write the ID of the node, say node number 8, and then you can simply write, if you want to know the name of the airport within the node ID, you can write node 8 slash, then you can just write name, and then it's going to extract the airport name. So it's much more easier to manipulate information using NetworkX this way. So let's go ahead and run this. We have a problem. Let's see what the problem is. The index is out of range. All right, I kind of figure out what the problem was. Is that I didn't use, go check the text-based version, and here I didn't update the different variables, so it was adding to the airport DB variable, which ended up creating this list out of range thing. That's why you guys need to check your variables before proceeding. Check the text-based version of this tutorial. I'll have the updated code is right there. So yeah, change these variables right here. I think I left here airport DB, and I put it as well the int, which the first record of the route. A route doesn't start with an int, so the conversion created a mistake, so it didn't add to the routes. Now everything is good, so you should have approximately 66,000 routes with like 900 errors. If you don't have that, go double check your code, go check the text-based version of this to have the updated version. All right, let's run this. This should work now. Name network is undefined. I have to rerun this, run this, everything is fine. Boom, boom. All right, now that we've added the different nodes, let's go ahead and add the edges. And in order to do that, it's kind of the same as well, the same process. So you go for every route in our route database, in route.-db. What we'll need to do next is for routes, now we need to add a condition. We need to add a condition. So if let's see, if the route, let's see, I think I'm gonna need to open the file because I need, let's see, where's the route description? It's right here. These two are in the graph basically, then yeah, we need to check them in the graph. So here's how it's gonna work. If the route.2 will be 0, 1, 2, which is our source airport in our network, is in our network dot nodes, right? And the destination airport as well, which is the next variable, the next slot, route.3 is in our network as well, right? Dot nodes. What we'll need to do is add an edge between network. We add an edge between the two airports. So network.add edge between a route at 2, the route at 3, and then we can add as well information about the edges, you know. Let's see, what can we add? We can add the airline as well that we save. Basically we can just add whatever we saved next, you know. We add route, like whatever is in the route. L9 is gonna be equal to, let's see, route, I think is the first one. Let me double check to be sure. Yeah, airline is the first one. Route.0, I mean the first slot. Then we can add, what else can we add? There is the airline ID, I think is the next one. Yeah, can add L9 ID is equal to route first slot. Yeah, and then finally we have what, I think I added the last two, which is basically the stops and the type of equipment. So we add stops, which is enable routes dot 1 2 3 4, yeah, route on the 4th spot, and finally we have the equipment that's going to be equal to route dot 5 on the 5th slot. And I think this is good. Everything should be good. Run this. Perfect. Now let's go ahead and double check a particular record. Let's see if these actually exist. Let's see. Let's check the 507. It should be London Heathrow Airport, 507. So to check a particular airport, now the only thing that you need to do is write network, you know, dot nodes, you know, and then you just, like a dictionary, just add the index of the node. What was the Heathrow one? Was 507, 507, and then let's run this. See, and then on the bottom you have all the information about that node. It is the altitude, it's alphabetical order. So you have altitude, you have the city, the country. So we have basically a bunch of nodes now that is our airport, and each node contains all of this information, you know. Now we can double check if there is an edge between a particular airport and another. Let's see, I don't know, let's try network dot edges, pretty much the same, and see if there is information existing between. Let's see what edge. Let's see, Heathrow 107, and I don't know what. Let's just try 20. No, there doesn't exist an edge with that. I don't know how to find one. I don't know, like that maybe. Nope, no edge between it. I don't know, 508 maybe. There's no such thing as 508. Now that's gonna be a trouble finding airport with edges like that. Maybe 100. Oh, perfect. There's an edge. So whenever there is an edge between a particular airport, you have the airline ID. You have the airline as well. Lufthansa, I think, is this one. What type of aircraft that's going and how many stops in order to go to that route. We can double check what airport it is. What is the airport number? 100. Let's try again. It's pretty much the same. Network dot nodes. Double check what airport is that. 100. So basically there is an edge between the London airport and the Canadian airport at Ottawa. It's operated by this airline. It's using this equipment, and so you guys get the point. So now we can double check, basically there's a way to see to get a list of basically all the airports that is adjacent to let's say the London airport, since we started with that. Figure out what flights and where the flights are going. So to do that, we can simply do this for the index in the list. Can find our neighbor, so that instead of just like guessing what ID to pick, we can just simply list the neighbors. So you can just do network, you know, dot neighbors, there you go. And then we want the neighbors to the London airport, which is 507. And then for every single one of these, what we want to do, we want to print the name of the airports, or at least the ID, the name or ID, I don't know, whichever we want. So let's go ahead and write network dot nodes of I, which is of every single neighbor. And then what do we want to print out? We want to print out, maybe let's print out the ID, right? And then as well, let's go ahead and print out the name. Let me add some space as well. In here, maybe add comma, and then we add network again, nodes, same I, then we add name. I think we're set. Let's run this. So here you go. So now we got a list of every single one of the neighbors, every single one of the airports to which London is connected to. So London flies to all of these, basically. So you have a flight to all of these airports going from London. So let's see if there is an edge. For example, if you want to have more information about what operates the flight from, let's say, to from London to, let's see, to, let's take, I don't know, the Chicago here International. So you can simply do this. We can just copy this, the edge dot, then we just put a 507, which is our London airport, and then we just add here the 3830, which is the Chicago here, and then we'll have it's operated by this airline VS. The airline ID is this. This is the type of equipment. I think a Boeing 343 or something like that, or Airbus 240. I don't really know what kind of plane is that, but you get the point. This is how we can get more information about a particular node. Another way to do that as well, right? Another way to get an idea, and you don't really need to write all of these for loops and everything. You can just simply write network. There's a function in NetworkX that does that, and it's called simply info. And you simply type it's not network, it's nx, sorry, it's nx.info, and you simply type your network, the name of your network. No, in our case it's just network, and then you type the node here. Let's keep on our favorite 47, the London airport, and then it's gonna give you this. The node 507 has the following property: the degree of the node is 170, which is the number of connected edges a particular node are. So a degree, I repeat, is the number of connected edges. That means the number of edges that touches that particular node. I didn't mean connected graph. It can be two-directional or single directional. It doesn't matter. It's just the number of edges that touches a particular node is the number of degrees. In our case, there is 170 edge. That means the London airport is connected to 170 other airports, and here are the different IDs for those airports. So basically, these, whatever you see here, was done by doing this, basically by this line, but the nx.info does that pretty fast. So if you want to grab as well the neighboring edges, you can simply do the NX info. Moving forward, you can as well check the density of a particular node simply as well. NX has a bunch of function like that. I really recommend you to check the different function that NetworkX is offering. Just simply type the density network. There you go. Have a 0.0007. All right, now what we want to do, right? We want to check if our network is actually fully connected, you know. So in order to do that, because we don't want part of the network, we don't want part of like some subgraphs or part of a network or that are not connected. We don't want to have just a single dots that are like just sitting there. We want a fully connected graph. So you can simply type the NX, which is NetworkX dot is connected. This is going to check if the graph is fully connected. That means every single node has a particular edge. Network run this false. That means that there are parts, there are nodes that do not have an edge, and for us to have a better picture of the different routes, you want to remove those airports that are like inactive, or I don't know, don't have edges for some reason. But before we do that, let's go ahead and check the degree centrality of our graph. Now the centrality basically measures somehow the importance of a particular node. For example, if you take the social network aspect, you realize that a page that has like let's say 100,000 subscribers is kind of more important than a page that has just about 100. So basically the centrality of a node basically measures how important the node is compared to the other ones, and basically it's just a fraction of the number of degrees it has. The more stuff are connected, the more edges are connected to a particular node, the more important it is in the eyes of the other ones. So in order to compute a particular centrality, centrality value, it can just let's just save like the centrality of the entire graph in in a variable called, let's call it degree centrality, pretty much as a variable. Let's see, and then we can simply call our graph. It's the same name basically, our function that network is providing, which is called degree centrality, and it's basically gonna calculate the importance of each node compared to the other one. So degree centrality of our network, yeah, let's run this. And now we can double check the various centrality our stuff offers. So we can simply save it as a new node. So for every, let's say, airport, which is every node, comma v, which is centrality value. Let's call it centrality value in degree centrality. So basically we're going to save the centrality in each node as a new variable, as a new piece of information, so that it can be used for later calculation. So degree centrality. All right, dot items, yeah, let's not forget that, dot items. Yep, then network, because the network works exactly like a dictionary, so we're just gonna add a new piece of information, as I said, which is the degree centrality. That's gonna be our value, and as the node, and the node ID, remember, is the first value that we take. Is going to be 1 2 3 4 5 5 6, is the row 0, is the airport 0 that we added. That's going to define our row, so we can just add airport. That's going to be our key, airport. So for example, what is this going to do is that it's going to go through every single airport and add the centrality value which is saved right in here. This is going to be equal to value because centrality to value. So remember, this centrality value, this is a dictionary. So basically it's gonna, in order to call something in the dictionary, you use this centrality value. So if we run this, okay, I know what the problem is. It's not that, it's not the network. This is supposed to be the nodes of the network, so I forgot to add the nodes. As we need the nodes, yep, they should work fine now. So so for every airport and centrality value in degree.centrality is going to be a dictionary that will contain first the airport ID and it's a related centrality value. So for those two, we grab the airport ID, that's gonna grab the particular node, and then we save its particular centrality value in a new I would say in a new slot within the new information piece. So let's go ahead and run that. Perfect. Now let's go ahead and check our centrality for, let's say, the London airport. Since that's what we're moving, we can simply call network dot the nodes, and then we're going to pick up our London airport, which is 507, I think, and then just add in this one. We need the centrality, and then you have a degree centrality of 0.024, which is kind of 2%. So this is the importance that of the London airport compared to the other one. So now the other function that's kind of interesting to have is to, as I said, so last time when we checked for an edge, you know, in the in here somewhere, network.edges, like you had an error that's coming up. So if you want to check actually if let's say two nodes have a pass, you can use simply this function of NetworkX that has path. So instead of receiving an error, you'll actually have receive either a true or a false based on the different values you put. So once again, we take our London airport, which is the 507, that we compare it to, let's say we said 20. This one didn't have a path, I think. Functional has path. No, that's not how you do it. Sorry, made a mistake. Has path. You need to add what? The network. Now you put the source in from, let's say, source equal 507 to, let's see, it's going towards the target, which is, let's say, we said 20. Now this should give you a boolean, which is false. It doesn't have a pass between those two airports, and we can quickly check as well something that did have a pass, which is 100 previously. So it's gonna give you a true. So that's a nice way to check if two like nodes have a path. You can use it in a for loop or in whatever you need, you know. So now, as I said before, we want to remove nodes that do not have any edges. So if you want to check whether a node has an edge or not, you can simply use the degree the degree variable, the degree function, the degree function, which is nx dot no, not nx. I don't think it's nx. I think it's the network actually. I think let's try this. The network dot degree. Degree should do it. Let's see. Yeah, and basically you have, when you do that, you'll have an overview of what nodes do and do not have edges. For example, node 13 just has 0 edges. It doesn't have no edges. So it's just a static point right there. So these values we do not really need. So we're going to go ahead and remove them. For example, the 13, there is the 17, there is the 35 that do not have, those are just stationary point because there's no edges that touch their degree is 0. So we can simply write a simple loop to remove these. Go and clean this network real quick before we can visualize it. So for every airport, let's say, and we need as well the degree, right? In let's say a list. Yeah, let's transform that to a list of network dot degree. Yeah, so we're basically going to transform whatever we see here as one, as basically as tuples, basically, I think. So now that's done, we can simply do an if condition. If the degree is equal to 0, we simply remove we simply remove the point. So network dot remove node will do that to remove the various nodes that you see. Remove node, which is our airport, that particular airport. So airports that have a degree of 0 will be gone. Let's run this. Perfect. Everything good, everything's fine. Now let's run again our info to see how many. nx.info, let's see, network, good. So now the average degree is 11. So each airport is connected to its other one 11 times. Excuse me a second. So each airport has an average of 11 airport who is it correct. Then again, it's an average. All right, and now that we removed all the nodes that have 0 as degree, we can go ahead and check if our graph is connected. And in order to do that, once again, it's the nx function dot is connected, and then we put our network up in here. Let's run this, and it's still false. We did remove all the nodes that contain 0, but we still have a connected graph. What does that non-connected graph, I mean, what does that mean? That means that there are subgraphs within our main graph that are connected between each other. So it's not a fully connected graph, but there are, for example, graphs that contain maybe like 2 degrees, maybe 2 airports are just have similar routes, like just 2 degrees, or so. There are basically little pockets of subgraph within our main graph. That's why our main graph isn't fully connected. So let's go ahead and check the number of disconnected component. We're going to see the number of subgraph we have, those so-called buckets, and to do that, NetworkX has a function that's called number of connected component, and then we add our network right here, and then we run this. We realize that there is 7 so-called subgraphs. You can go ahead and check them. I think you can check them using this. Let's see, connected components, and then we add the network up in here. No, you can't do that. It's connected annex. I think I might have come. Oh yeah, here. That's a mistake. The components. No, so you'll just have an object. So usually whenever you have this, that means you're supposed to loop through it. And right now I'm just interested about the size of those components. So in order to take them out, let me just use a list comprehension real quick. We need the length of let's say elements for elements in connected graph. Yeah, this should pull them up right here. So as I said, we have 7 subgraphs. Like we have a big subgraph that contain like around 3,000 airports. Then you have 10 airports that share kind of the same connections, same pocket, but are not connected with the other one. So these 10 airports are just kind of a small sub network that are not connected with the main ones, which is this 3,000, the largest one. So what we want to do, right, is that we want to take into consideration this, create a subgraph that contains just these ones, and then we're going to disregard the rest of them since they're so little compared to the other main record. So we first need to grab this. So we'll call it I don't know, main subgraph, I guess, main subgraph. And in the main subgraph, we're going to grab the maximum number. We can just use the max function easily. Max of nx connected, max of this basically. And then we'll use as a key the length, since comma, and we use as a key the length of those records. So let's see, everything should work. Nope, length isn't. Oh no, I mean not length here, it's a key. The length. Perfect. Now we're going to create a subgraph, which is, as I said, a portion of the main graph, and then we are going to call it I don't know, network, call it main network. And the main network is gonna be basically our network, right? Subgraph, network dot subgraph, and as argument is going to take this main subgraph. Subgraph. Now let's run this, and then let's get some info about the main network at next.info, see if everything was grabbed. Network main, let's run this, and next send for, let's see if it's not defined. Let's see if I wrote it properly. Next work, yeah, I didn't want network, I wanted network, not next work. That's what it is. Boom. So we have number of nodes 3077, the number of edges 18,000, and the degree is about 12, 11.9. Now let's actually see if that's actually a connected graph. And to do that, let's see, where is the function? It's this one, is connected. Let's see, network main, run it. Perfect, true. That means every single element within our network is connected. This is like we want it. Now we can go ahead into our final step, and then we are going to visualize this data.